Welcome back to my favorite people. Last lecture, I went through effect of solvent on SN1 and SN2 chemical reaction, and we said for SN1 or E1 chemical reaction, we need the solvent to be protic solvent. While for SN2, we need it to be a protic, a solvent with at acidic H. And we ended with this. We said that overall for SN2 chemical reaction, you need to have a polar protic solvent. And for SN1 chemical reaction, you need to have a polar protic solvent and a solvent with acidic H to stabilize the intermediate. Okay, now let's talk about the living group by themselves. And so when it comes to SN1 or E1, we say rate of the reaction is equal to K multiply concentration of the substrate to the first. That means the nucleophile will not be effective because it will be added in a step that is way faster than the rate determining step. And rate determining step to break a halide bond with carbon. And now, the carbon fluoride bond is shorter than carbon iodide bond. Okay, as we move from down, as we move down inside the group, the halide group, the bond will be longer and longer, and because it will be a longer bond, it will be easier to break it. Okay, so breaking the bond is easier. That's one. Okay, so breaking CF bonds is harder. Okay, harder. That means it requires more energy than CI bond. That's one. Okay. So you will be spending more energy to break CF than CI. Now, what will happen to the intermediate, to the halide by itself, say having fluoride F-1 versus iodide -1, iodide because it's a bigger object than iodide, than the fluoride. Fluoride with a negative charge is going to feel too much repulsion between the new electron and the electrons of the fluoride by itself versus iodide. Iodide is a bigger object, so it can easily accommodate that electron, and iodide will be more stable. So this one, it will be more stable. So the living group by itself will affect rate of the reaction. And if you can break the alkyl halide bond faster, your rate will go up. Okay, next, let's talk about the stereochemistry of E1, the SN1 E1 chemical reaction. Okay, now, first step of this chemical reaction is to create a carbocation. Now, what will happen to the carbocation after, formation? It can go through SN1 nucleophilic substitution, first order, or it can go through elimination, and again, first order. And in this case, I have a halide that's attached to carbon, and our carbon is a tertiary carbon. We have water, and water, it will be the solvent. So we are talking about technically solvolysis. That means the halide will be taken from the system with help of the solvent. And we are using heat to speed up the reaction. So for your knowledge, heat will kind of like push the reaction to elimination. Every time you see heat, there is a higher chance to get elimination product. Okay, now what will happen if we lose the halide? We get this intermediate. We get a carbocation that is a tertiary carbocation, and this tertiary carbocation, if this one goes through elimination, we can have two products. We can get two products. One, here we have hydrogens that they are identical. Those two hydrogen are identical. And also we have a beta hydrogen on this carbon. Okay, so those two, I'm going to call them 1, and this one I'm going to call it 2. So we have two betas. Let's call this one beta 2, or yeah, let's call it beta 2 for now. And this one is beta 1, beta 1. Okay. Now, if I remove hydrogen from the beta 1, okay, one of the products that I will get, it will be this. I will have a double bond here. Okay, so I get the double bond there. And here I have a methyl. Okay. That's if we go through beta 1. So we removed hydrogen, one of the hydrogen and H1, or like we have two of them. So let's say we went after this hydrogen and we got such a product. Or we can go after second hydrogen, let's say beta 2. And in this case, the product we'll get, it will be like this. So we will have a double bond, it will be there. Okay, the question is which one of this is more stable? Okay, and first one, we have double bond with less substituent. The second one is a double bond with more substituent. So this one, it will be the Zaitsev product. The Zaitsev product, while the first one, it will be Hoffman products. The one with less substituent, we call it Hoffman product. With more substituent, Zaitsev product. And which one is more stable? This. So we say a reaction is creating technically two products. One of them is more stable, okay? And because it has more substituent to donate electron to the double bond technically. And that's the reason we call it more stable than the Hoffman. And question here is going to be, what's the meaning of reduced selectivity? If your chemical reaction can we create two isomers, and one of this isomer it will be preferred over the second isomer. Okay, in that case, we say you have reduced selectivity. When I say isomer, you should have different connectivity. Be careful about it. So we have a chemical reaction that is creating two isomers through different connectivities. And so in this case, we say the reaction prefer one of the product, and we call it reduced selectivity. One region will be preferred over another region. One carbon will be preferred over another carbon. Which carbon? So we have these two carbon. We have this carbon versus that carbon. Which one is preferred? The one that has more substituent. Okay, the one that has more substituent will be preferred, and so I'm going to say the Zaitsev product, it will be the favored product. Okay, now, and here I have a tertiary carbocation. Sorry, I have a tertiary halide, and in the presence of heat and solvent, again, we can get such an intermediate. So let's say this is going to lose. Okay, this one is going to lose the bromide. Now we have a positive charge here. So we have a positive charge and plus bromide -1. Okay, next, I'm going to say this carbocation is a tertiary carbocation. And now what will happen to the tertiary carbocation? The tertiary carbocation might lose some hydrogen. And now we have two options. Okay, we have one hydrogen is here, that hydrogen, and also we have two hydrogens there. And these two hydrogens are the same. So let's call this one 1, call that one 2. Okay. Now, if we take hydrogen, if we remove hydrogen from the, let's say, from number 1 product we will get, it will be like this. So we will have a methyl here, and double bond is going to be either here, which is going to be equal to this. Okay, it's going to be equal to this product. So again, let's put the double bond on the right side. Okay, so these two are the same. Okay, I just simply change position of the double bond. Okay, or okay. If we take one like number 2, But so if I take number 2, this is going to be the product. And so we will get carbon attached to this, and a double bond will be here. Okay, so now let's highlight the double bonds. We have a double bond here, which is equal to that one, and another double bond there. Which one has more substituent? And the two on the left, they have more substituent, so they will be the Zaitsev product. This one will be the Hoffman. Okay, and the one with more product, more substituent, it will be more stable. Okay, now, is there any way to tune the ratio between Zaitsev and Hoffman product? When it comes to, when it comes to E1, we don't have much control. Okay, why we don't have much control? Because when you need to ask yourself when this chemical reaction is going to happen. This chemical reaction is going to happen after a slow step. The first step, it will be slow. That means this is going to be the rate determining step. Well, the second step, it will be fast. So any of this is going to be a fast step. And if it's a fast step, you're not going to have much control to it. You are not touching rate of the reaction. Okay. Whenever you add the nucleophile to take hydrogen from the system, you're adding in a step that is fast enough. It's way faster than rate determining step. So you don't have really control on rate of the product as E2. Okay, let's go through E2. I want to just remind you how was E2. In E2, you have a base. Your base is really strong base, and that base it might go after, for example, this hydrogen, or it might go after one of those two hydrogens. Okay, if we go after any of, let's say, any of this hydrogen. Okay, if we go after this one, okay, and what the product we will get, it will be like this. We will have carbon here, and the double bond, it will be there. Okay, or we might get actually a double bond here, and that means carbon is going to be there. Okay, so this one will be Hoffman, and the second one, it will be the Zaitsev product. And your base is a small base, and because it's a small base, it can make it to primary or a secondary carbon. It can easily grab hydrogen from them. Now, if you make the base bulkier, so for example, okay, instead of using hydrogens for methoxide group, I'm going to replace them by methyl. And remember, methyls are bulkier than hydrogen because it's a carbon attached to 3 hydrogens. So this one is going to have huge steric effect, and because it has a steric effect, it cannot make it. It cannot make it much to, like the secondary carbon. It will prefer primary carbons, and so the main product will be the Hoffman product. So this is going to be the main product, and again, let's highlight it. And when it comes to Hoffman, ratio is going to be really low. And in this case, I will say this is going to be the major product. And that one, it will be minor. Okay, why? Because I use a bulky, base. So my base, because it was bulkier, I managed to switch from minor to major product. So I had the control to rate of the product. And like the first one, this one used to be major. Now it turned to minor product because we used a bulky group.